Hello once again, class, and welcome to the legendary unit circle mock lecture. Well, the unit circle is legendary. I don't know about this mock lecture, but today we're going to be specifically constructing the unit circle, looking at how we can use it to redefine sine and cosine, and then also what do the graphs of sine and cosine look like generated from the unit circle, right? How do we graph them on the Cartesian plane? So first we're going to talk about the limitations of the definitions of trig functions that we have right now, which is the way that we define them is that they're ratios of side lengths of a right triangle as our output of the functions, and then the input is an internal angle theta inside the right triangle, but theta is not the right angle, right? It's one of the other two angles that are inside of the triangle. Now, because of the way that we've defined this, theta has to be in the interval 0 to 90 degrees or 0 to pi over 2. If you're not familiar with this notation, this is a domain notation essentially. This means in, right? So theta is in this. So if we rewrite this another way, we could say the domain of any of the 6 trig functions right now, again, the way that we've defined the functions now, is 0 to 90 degrees or 0 to pi over 2. Now you might be thinking to yourself, Mock, why? Why is that the domain? Why can't we go outside of those bounds? Well, think about a triangle. If this is the angle measurement theta, or maybe it's this one, doesn't really matter. Theta is always an acute angle, right? If we try to make it obtuse by bringing the internal angle something bigger than 90 degrees, you get this shape. But that's not a triangle when theta is bigger than 90 degrees. I mean, honestly, even when theta is 90 degrees, right? That's not a triangle either, right? It's like a half of a box or something. You also can't bring it to 0, right? If you bring the internal angle down so that it's coincident with its initial side, so the initial side and terminal side are the same, right? That's not a triangle, right? Or even if you bring it past, right, the initial side. So then this is the angle measurement theta, right? That's not a triangle either. So there exists, by the way, that's what this means. There exists a problem with how we've defined the trig functions so far, right? As just hypotenuse over opposite, or opposite over adjacent, or adjacent over hypotenuse, or whatever it is that we're defining. So to state it very clearly, the goal of this video is to use what we know about right triangles to redefine sine and cosine, and by extension, the other trig functions, right? So like, this is going to be true for cosecant and secant and tangent and cotangent, so that the domains can be extended. We want to be able to plug anything we want, right, into at least sine and cosine for now. And that's why we need to learn about the unit circle. All right, so first we're going to construct a unit circle. You draw a circle centered around the origin with a radius 1. All right, thanks a ton for watching, and I'll see you in the next video. I'm just kidding, obviously. That is a unit circle. It is not the unit circle, right? But a unit circle, by definition, is a circle with a radius of 1 unit. But it's the coordinates around the circumference, right, of this circle that we really care about. If you draw a radius anywhere, right, we can call its coordinates AB, or XY. I call them AB here in this example, but A is the X coordinate, and B is the Y coordinate. Which means that this right triangle that I've kind of outlined here has a height of B and a base, there we go, a base of A, okay? Now and we know the hypotenuse is 1, okay? So if we call this angle measurement theta, then let's just find sine and cosine. What is the sine of theta? What is the cosine of theta? We're going to start with cosine. Well, cosine is adjacent over hypotenuse, so it's A over 1. So check it out. Cosine theta is A. It's this thing, right? Cosine theta is the x coordinate of a point on the unit circle's circumference. Similarly, sine of theta, which is opposite over hypotenuse, that's B over 1, that's B. So B, right, the y coordinate of the unit circle is actually just sine of theta. And these are going to be our definitions, our new definitions for sine and cosine. So the new definition for cosine is that it is the x coordinate where the terminal side of angle theta intersects the unit circle. And the new definition for sine of theta is the y coordinate where the terminal side of angle theta intersects the unit circle. And of course, we're talking about angles that are in standard position here because we're on the xy plane. So this is how I think about cosine and sine moving forward. X coordinate of unit circle, y coordinate of arbitrary point on unit circle, right, respectively. And it can go anywhere we want, right? We can put it in quadrant 3, and this would still be the cosine of theta and the sine of theta, right? So we're going to make some observations about these new definitions. The first one is that we can literally plug any real number into this thing now. You know, we could plug in an angle measure between 0 and 90, right? But we were already able to do that before. But now we can plug in angle measurements that are between 90 and 180. We can plug in angles that are between 180 and 270, right? Between 270 and 360. We can exceed 360, right? We can make whatever angle we want, and positive or negative, and the x coordinate of the unit circle and the y coordinate of the unit circle exist, right? And so there's an output for any real degree measurement or radian measurement that we plug into these functions now. Also, we can clearly see the range of both sine and cosine is -1 to 1, right? You can't get further away from the origin than 1 on something that's got a radius of 1. So when they're exactly in line with the y or x axis, then you're exactly 1 unit away, either in a negative aspect or a positive aspect, right? Verticality stuff here, that's sine of theta, because that's associated with the y coordinate. The horizontal movement, right, that's associated with cosine, that's the x coordinate. But the x coordinate can only be at most -1, at least -1, and at most +1. We can also see which angles give us negative and positive outputs. So again, since cosine is associated with an x coordinate, we know that cosine is positive, for example, in quadrant 1. So is sine, actually, because we're in quadrant 1. This is the positive axis of y and the positive axis of x, right? In quadrant 2, cosine is actually negative. Sine is positive. So if you plug in something between pi over 2 and pi, or between 90 and 180 degrees, the cosine of that angle will be negative, right? The sine of that angle will be positive. Similarly, in quadrant 3, so we're now between pi and 3 pi over 2 for radians, or 180 and 270 degrees, that's both sine and cosine are going to give you something that's negative. And then finally, rounding everything out in quadrant 4, both cosine, oh man, there's a typo here. Sine is negative in this quadrant. Yeah, cosine, I want to point that out. Sine is not positive in quadrant 4, sine is negative. Also, we can see that special right triangles, we can use special right triangles to fill out exact key values of sine and cosine to help graph and evaluate the function without the use of a calculator. So, we just finished up talking about special triangles, and we're immediately going to see that their application helps in constructing the unit circle. So again, because the x coordinate is the output for cosine, just look at the angle measurement that you're plugging in for the input to figure out what input-output pair you can make for cosine and sine respectively. So for example, the cosine of 0 degrees or the cosine of 0 radians is 1, right? Because we haven't moved anywhere, right? Similarly, actually, and I'll get to this in a little bit, the cosine of 360 degrees or the cosine of 2 pi is also 1. The sine of 0 or the sine of 2 pi, that's 0, right? Because the y coordinate at 0 radians or at 2 pi radians or in fact at -2 pi radians or 16 pi radians is also 0. Okay, so cosine 0 degrees is 1, sine of 0 degrees is 0. Let's move to 30-degree angle measurement. I've constructed a 30, 60, 90 triangle, effectively, right? Because we know the specific exact side ratio measurements for 30, 60, 90, we can fill out what cosine of theta and sine of theta are. We can fill out what the cosine of 30 degrees and the sine of 30 degrees are. Now, granted, the picture that we have is a little bit more scaled down than the 30, 60, 90 ratio stuff that we set up in the last mock lecture, insofar as it's actually the hypotenuse that's 1. So this is really 1. But that's fine, right? Because one of the things we learned is if we know one side length of a 30, 60, 90 or one side length of a 45, 45, 90, we can fill out all the other ones exactly. For example, the height should be exactly half of this hypotenuse. So we know that y should be a half. We know that the short leg, or rather the long leg, is the square root of 3 times whatever this measurement is, right? So if this is 1/2, then the blue length, the x coordinate, is going to be 1/2 times the square root of 3, which is just the square root of 3 over 2. So we know that the cosine, right, and this is really the main idea, the cosine of 30 degrees is the square root of 3 over 2. The sine of 30 degrees is equal to 1/2. Okay, that's what x and y coordinates are on the unit circle. They're the cosine and sine of the internal angle, of the central angle that you're looking at here. The next measurement we can look at is 45 degrees, right? This is a 45, 45, 90 triangle. Again, picture's a little bit different, right? It's a little bit scaled down from the original picture. But we know that whatever this is, just divide that by the square root of 2 to get this side length, right? So I'm going to take 1 and divide it by the square root of 2. Now, typically, in a lot of trigonometry books that you look at, or most videos that you watch online, are going to rationalize this denominator, right? Mathematicians don't like to have irrational numbers in the denominator because it's hard to answer the question, how many times does this irrational, non-repeating infinite decimal go into the exact number 1? It's hard to say, right? Exactly. So we can rationalize this thing, and we would get the square root of 2 over 2. That is the sine and cosine of 45 degrees. They're exactly the same thing. Sine of 45 degrees, square root of 2 over 2. Cosine of 45 degrees, also square root 2 over 2, which brings us to the next exact angle measurement, which is 60 degrees. Again, this is part of a 30, 60, 90 triangle. So using similar logic that we did for the 30-degree central angle, we're going to do the same thing to figure out that the coordinates are basically just flipped, right? So we flip these things. It's now the cosine of 60 degrees that gives us the 1/2 measurement, and the sine of 60 degrees gives us the square root of 3 over 2, which brings us to 90 degrees, where we know the cosine of 90 degrees is 0, and the sine of 90 degrees is 1. That is known as quadrant 1 of the unit circle. Now, I know you're thinking, oh my gosh, are we going to have to do the same thing for quadrant 2, for quadrant 3, and for quadrant 4? Yes. But also no, because we're on the Cartesian coordinate system, and you can literally just reflect some points over the y-axis, right? So the sine of 120 degrees, still positive, square root of 3 over 2. Since we're in the same, it's literally the same height, right? Cosine of 120 degrees, though, that's now negative. And the reason we're allowed to do this is because we're still constructing a 30, 60, 90 triangle. Right? This is 90, this is 60. So all those side lengths still work, right? All those ratios are still fine. You just have to cognize, well, now, wait a minute. This is a position, it's a location on the unit circle, it's a location on the Cartesian coordinate system. That's got a negative value here. So the cosine of 120 degrees is now negative 1/2. And if we reflect all this other stuff over, we get similar stuff. Y coordinate's the same. X coordinate is negative, though, right? When we get to 180 degrees, right? The cosine of 180 degrees is negative 1. Sine of 180 degrees is 0. To fill out the whole bottom half of the unit circle, we just reflect everything, which basically keeps the x coordinates what they are as you reflect down, but changes all of the y coordinates to being negative. All right, so this is what we get, and this is, in fact, the completed unit circle. I would you know what you should do? You should draw this on a piece of paper and hang it up in your room, right? Frame it if you want. You want to memorize the unit circle when you're taking a trigonometry or a calculus course. In fact, I think it's just generally a good idea to know the unit circle anyway. Like, what if you're standing in line at the bank, maybe when the pandemic's over, and like a robber comes in and is like, I'm going to rob this bank unless someone can tell me what the cosine of 2 pi over 3 is. You're going to save the day because you're going to be like, it's negative 1/2. You just saved lives, okay? Just by knowing the cosine of 2 pi over 3, you just saved an entire bank's worth of lives. Congratulations, right? You're going to be on the news. They're going to print an article about you. Person saves the day because they know the unit circle. Amazing. Anyway, getting a little off topic. Let's get back to it. Now you can use the unit circle to graph sine and cosine, and it's actually really cool how this plays out. So I'm gonna draw the cosine graph in this top grid. I'm gonna graph the sine graph in the bottom axis here. And we're just gonna go around the unit circle. The inputs in radians are our x coordinates, right? The outputs, right? The x coordinate here on the unit circle, the y coordinate here on the unit circle. That's what I'm going to graph as the y coordinate for the graph of cosine and sine. So at 0 degrees, cosine is 1 and sine is 0. And all I'm doing is I'm reciting. I'm like, okay, well, cosine of 0. So we're at 0. That's 1. So I put a little point at 1 up here, right? Sine at 0. So we're at 0 is 0. So I put a point at 0, 0. And then I'm just going to go around the unit circle. So at pi over 6 at 30 degrees, which is about here. Not exactly, but it's somewhere there. Cosine is square root 3 over 2, which I kind of estimated where that is. Sine is easy because that's a half, so it's exactly on the half mark. Moving to 45 degrees, or rather pi over 4, since the x coordinate here is in radians. Cosine and sine are both square root 2 over 2, so they're at the exact same height here on the y-axis. So they get a point there. Pi over 3, it's cosine's turn to be a nice exact value. It's a half. And then sine is the square root of 3 over 2. So you'll notice that the cosine of 30 degrees, about here. The sine of 60 degrees, also at that same point, respective of their graphs. And then we get to pi over 2, where cosine is 0 and sine is 1. And we're just going to repeat this pattern. And actually, at this point, I started just looking at the nice whole number values, so you can get a more clear idea if you were to plot these things here. But I'll graph the thing with a nice curve when I go through it. It's just really tedious to estimate these specific values, so I didn't do it for the next ones that we're graphing. So at pi, cosine is -1, so it's way down here. At sine of pi, we're at 0. Then at 3 pi over 2, cosine 0, sine is -1. Then we go to 2 pi, and we're back where we started. Okay, so we get a graph that looks like this for cosine and sine. And at this point, sine and cosine just start repeating themselves. They're cyclical functions. They start just doing the same thing over and over. So we describe them as periodic, in the sense that this is the amount of time that it takes for it to return to its original position. And then that just starts repeating itself over and over and over. So the period, or the wavelength, which is it sometimes is called, is for cosine and sine 2 pi. It's a full revolution around the unit circle before it starts repeating its values. At this point, things that are coterminal with these specific values just get the same x and y coordinates, right? So if I were going to graph 3 pi, that's coterminal with pi. So the cosine of 3 pi will be -1. The sine of 3 pi will be 0, right? 5 pi over 2 is coterminal with pi over 2. So cosine gives us 0, sine gives us 1. Then we're at the 2 pi, or the 3 pi rather, which gives us 0 for sine and -1 for cosine. And then you can also go the other direction, right? Negative pi over 2 is the same coterminal angle. It's the same angle as 3 pi over 2, right? So it's going to have the same values for sine and cosine at 3 pi over 2, which is 0 for cosine and -1 for sine. Negative pi is coterminal with pi, so we get the same values as cosine pi and sine pi as we do for cosine negative pi and sine negative pi, right? Negative 3 pi over 2 is coterminal with pi over 2, so we get the same values as pi over 2 there. And negative pi over 2, now we're back to where we started, but in a negative direction. And so this is the sine and cosine graphs. If you overlay them, you can see that sine and cosine are really just a pi over 2 shift of one another, right? If you were to take the cosine function and shift it pi over 2 units to the right, it would line up exactly with the sine function. So the unit circle can similarly help us evaluate certain coterminal angles outside of the interval 0 to 2 pi now, because we have a graph, right? A cyclical graph. It just comes down to looking at what is the angle that we're looking at coterminal with, and then we just basically recite that specific x or y coordinate, whether we're evaluating cosine or sine. All right? But we're going to do that in the next video. Okay? So hopefully this video was helpful. If you have any suggestions, leave them in the comments or send me an email. Thanks a ton for watching, and I'll see you in the next one.